Good morning. We are headed now into kind of a whole new set of topics in some way. We've been looking at electric fields, magnetic fields, DC circuits, AC circuits for a number of weeks now. And now we are going to move into looking at light and the properties of light. So chapter 31, previous chapter, we had a chance to do a little bit of a transition showing how the propagation of electric and magnetic fields actually is light. And so let's talk about some of the properties of light. Let's go ahead and get started. So we're into chapter 32. Here are the topics that the chapter is going to cover. But let's get in and take a look at some properties of light. Now, we're going to be looking for a couple chapters of what we call the geometric properties of light, or geometric optics. And so in geometric optics, we're just thinking of light as traveling along straight lines and reflecting off surfaces and such. And then we're going to move into quantum optics. We're going to use some quantum mechanics or quantum physics to look at the interference effects of light and discuss in more detail light consisting of particles that we call photons and how these photons have interference properties to them. Anyway, let's take kind of a basic standard geometric optics approach. So here's an object. It's a pencil and it's been sharpened, and what it's showing is that when an object is illuminated, light comes off the surface, and in general the surfaces are a bit rough, and so light's coming off in all different directions. And that means that, when we're looking at an object, I can kind of walk around the object and I'm able to see light coming off the object in all directions, so I can actually view the object. And we can think of the light as traveling in straight lines. So that's kind of our geometric optics approximation, is that in many situations this model works really well. It's a bit of an idealization, we'll find out, but in many everyday cases this is a really good approximation. So here's some light going into this person's eye, and the light's coming off the object. Now when we have surfaces that are really smooth, what we find is that light coming in off that smooth reflective surface ends up preferentially reflecting off in one particular direction. And so what we say is that the angle of reflection equals the angle of incidence. So the picture we have here is, here's this smooth surface. Maybe it's part of a mirror, for example, or it's the surface of water that's really smooth. And here is light coming in from a particular direction. And what we do is we draw the normal to the surface. Again, this is another example of representing the surface by looking at a direction that is perpendicular to the surface. Now, relative to this normal or perpendicular, there's going to be an angle of incidence, and that's labeled as theta I. And then there's going to be an angle at which the light preferentially reflects. And that angle is listed as theta sub r. And if we have a really nice, shiny, smooth surface, something like the surface of a mirror, the angle of reflection matches the angle of incidence. Those two angles are going to match. Okay, and yeah, I guess I'm trying to decide what picture A and B, how they're different. I think they're both showing the same thing. Incident light ray, reflected light ray. Okay, I think they are. You guys let me know if you see anything difference between those two pictures. So what we're saying here in this diagram is that for most surfaces don't have, when we look at the detail, they don't have a really smooth surface to it. So we're seeing light come in and reflect, but because the surface has these variations to it, the light comes off that surface in all different directions. This is called diffuse reflection. compared with the smooth surface we were seeing before. So here is reflection off of a mirror. So we're going to say here's a mirror. Now they're calling it a flat mirror. That also goes by the name of a plane mirror, where in the geometric sense a plane is something that's completely flat. So here are two plane mirrors. They're completely flat. They're tipped at 90 degrees compared with each other. What we're going to do is we're going to shine a light in. Now this is different from what we just observed. Let me look at the picture here. Remember, what we said is when we have light reflecting off a surface, officially we define the angle relative to the normal, not to the surface itself. So here they're showing that the light's coming in at an angle of 15 degrees relative to the surface, but the angle of incidence would be defined as 75 degrees. So that's a 75-degree angle of incidence. Now, what they want us to do is to go in and follow the path of light and say where everything's going to end up. So, if the reflected angle matches the incident angle, then theta 2 equals theta 1. So this is 15 degrees, the complement is 75, this would be 75, this would be 15. Now that's a 90-degree angle. So it's specific. This problem is we're looking specifically at something at 90 degrees. And so if this is 15, that's going to be 75, and this is going to be 15. So theta 2 and theta 3, if we work our way around all the angles, are actually complements of each other. So this is 15 and this is 15, and this is 75. Now, if this light is coming in at 15 degrees compared with the horizontal direction, look, the light exiting is also coming out at that very same angle. So, let's see. So yeah, I think what I did is I kept all the thetas, theta 1, theta 2, theta 3, theta 4, but what I did is I introduced alphas, which were complementary, and if that angle is at 90 degrees between the two plane mirrors, then yeah, the light coming out is going to be anti-parallel to the light coming in. I didn't quite get that drawn exactly right, but you can kind of see the effect. Okay, so that's kind of the first thing we want to do is look at a flat plane surface. A mirror is kind of the ideal that we're thinking in terms of. So here's another example with a plane mirror, where plane means completely flat. So here's a person, they're looking into a mirror. Now, I'm guessing you guys have some experience with this. So you've got some experience at standing in front of mirrors and then looking into the mirror and kind of looking around in the mirror and saying, oh, that's interesting how that works, right? You would think, knowing that a person that has never experienced looking into a mirror, that would be remarkable for that person to come up and just kind of look around and go, oh my gosh, what is this mirror doing? Anyway, what they're pointing out is that when you look into a mirror, here's an object sitting on a counter. And I look into the mirror, and I can see that, I can see the objects right here, but I can also see an image that is being formed. So because of the reflective properties of the mirror, not only, the object is still here, but there's what we call an image of the object that isn't really there, right? What the image represents is the effect of the reflected light. So here is the object itself, the actual object, and light comes off this object, reflects off the mirror, so that the light coming into my eye appears to be coming from this location, and so we experience that as an image. This pattern of light right there, I'm going to call that the image light. So the light coming off the object, that's the object light. The object light would have continued in this direction, but there was a mirror, and so the light got reflected. And so what we see is image light, and so we have this experience of, hey, there's an image located back behind the mirror over in that direction. Now they're doing some geometry here, and we'll come back. I think we can do this a little more simply. But a couple things we want to start defining here. This is referred to as an object distance. The distance out to where the object is located from the mirror surface itself. We're going to call that DO. And then the image, the measured distance from the plane of the mirror itself, the surface, out to where the image is located, we're going to call that the image distance. So those are our first two definitions here, object and image distances. Now, the image, in this case, is referred to as a virtual image. Let's go back and take a look at that. The light coming from that image, notice that the image light is right here, but that image light never comes from this location. So because of the way the light's reflected in this particular example, the light isn't coming from the image. We call that a virtual image. So we'll see examples of real images where the light really does come from that location. But in this case, the light's not, it never actually reaches that location. Now, funny enough, we also have, we'll see examples of what we call real objects and virtual objects. Now, this is a real object, and that's because the light is coming away from the real object. But what we'll find is if we have a series of mirrors, or in the next chapter we're going to introduce lenses, if we have a series of mirrors and lenses, each mirror or lens, we start out with an object, and then the light gets reflected, and we end up with an image. The image from that becomes the object for the next lens or mirror, and so we'll see examples of where the object can be real or virtual, and the image can be real or virtual. We'll see this in lab too, so we'll get a chance to experience what these real and virtual images and objects are. Now, we've looked at some examples. Let's see, we started off with the easiest examples. Those were the plane mirrors, where the mirror was just flat. But now we're going to move on, and for a lot of optical devices, we make use of curved mirrors. So instead of having this be flat, we're going to have a curvature to it. Now, these are shaped like sections of a sphere. So I don't know if these diagrams are quite representing that. They're representing cross sections. So what's happening is it's a portion of a sphere where, part of the mirror is curved, and so the light coming in, let's say we have light coming in from a distant source, far, far away, and the light's coming in, roughly parallel. When it strikes this mirror, because of the curvature, we don't get the light coming straight back. The light coming away from the mirror is diverging. So we can say that's an example of a diverging mirror. And diverging mirrors have a shape. The shape of that surface, we say, is convex. So the convex specifically refers to the fact that the mirror bulges out towards the direction where the light's reflecting. So this surface that's bulging out is called convex, and a convex mirror creates a diverging effect. So the mirror is diverging. Now, the other possibility would be to curve this mirror the opposite way. So this shape, this geometry, is referred to as concave. And of course, you're always told that the easy way to remember these is this is kind of like a cave. It caves inward. And so that shape is concave. Bulging out, this is, what is that doing? Is it vexing? Is it bulging out? That's a vexing, anyway. So this one's convex, this is concave. And for mirrors, the concave geometry creates a converging mirror. When we get to lenses, we'll find out that this reverses, and we'll see why. But for mirrors, right now, the convex shape gives us a diverging mirror. The concave shape gives us a converging mirror. All right, and again, the way we're going to define this is having light come in that is parallel. So we have light coming in that's parallel, and light coming in parallel is equivalent to a source or an object that is far, far, far away. We say that it's effectively infinitely far away in that limit the light comes in parallel. Okay, like this tree, right? So here is the tree. It's being illuminated by sunlight, and let's just take that one point. Light from there is going in all different directions, right? Every part of the tree, the light gets reflected out in all directions. But what happens is, you can see when I look at the tree, I go, oh, that light's spreading out from that point. But by the time I get far enough away, the lines kind of look like they're parallel, right? So in the limit, where the objects are far, far, far away, the light coming in can be thought of as coming in parallel. Now what this does for us, it defines what we call a focal length. And that's kind of our next definition here. If we have light coming in parallel, all right, what kind of mirror do we have here? Is this concave or convex? And it's concave. And is the mirror converging or diverging? And we can tell, I mean, the light's coming in parallel, but coming off the surface, the light converges. Now, what they're showing with this diagram is, if we take all this light coming in, and we make this surface, if we make this a spherical mirror, so again, the curvature here is as if it's part of a sphere, what we find is that the light coming in doesn't focus at just one location. What we would like to do to get a mirror, to have the, the properties of a mirror where we can look at it and view an image that is in focus, we need all these lines to come together at one point. How can we make that happen? In fact, they're saying this is an effect called spherical aberration. What we do is we cut away the outer regions of the mirror. So rather than using a large spherical shape where there's a lot of, the surface is really bowed inwards, we can keep the same curvature on the mirror, but we just cut it out so that these outer regions go away. And what that does is it eliminates this stuff and gives us a sharper focus. So most spherical mirrors actually only spread out over a few degrees of curvature. Okay, so if we think in terms of the center of curvature for this, so if the center of the curvature is out here somewhere, we're finding out that it's only sub-tens of several degrees of that angle. Okay, so what happens when we do that? We cut the mirror back a little bit, and now we're going to say that to a good approximation, we have all the lights coming in, and off these several degrees of curvature that we have, everything is coming to a sharp focus, and we call that the focal point. We are going to do diagrams. We're going to do diagram drawings of these. So in these ray diagrams, these light diagrams that we're looking at, the focal point will become an important point to identify. Now for mirrors, what we can show is that if there's a center of curvature, so this is actually the center of curvature, meaning that there is a radius from that out to the surface of the mirror. So have they drawn this right? It doesn't look quite perpendicular. So they're claiming, I don't think they quite got the curvature to match. They're claiming that, and that's what we're trying to show, is that if this is a spherical mirror, then there is a center to the sphere, and that's just a small portion of the spherical surface that we're using as the mirror. That represents how much curvature it has, so that has a radius of r. Now what they've shown is that this is theta and this is theta upon reflection. Then to a good approximation, the focal point, in terms of distances, the focal point will be 1/2 radius away from the surface of the mirror. So that distance is called the focal length. So we have a focal point and we have a focal length. And the focal point is a point on the drawings, the diagrams that we make, and the focal length is going to show up in some formulas here in just a minute. So again, the focal length is going to be 1/2 of the radius of curvature. And then just for reference, this is the principal axis. So if we take a line that runs perpendicularly right into the center point of the mirror itself, not the center of curvature, but the center of the mirror itself. That's a principal axis. That's just a reference axis that we use in our drawings to help guide us. So here it is. The focal point, or the focal length, rather, is going to be 1/2 the radius of curvature. Now, this has switched over. I think I switched that to big R. I think of the radiuses as a big R, not a little r. Okay. And then they're pointing out here that if you really are looking at objects far, far, far away, you can, instead of using a spherical surface for the mirror, you can use a parabolic surface. And it's a little different shape, and if it's parabolic, then you do get a nice sharp focus even for distant objects. And so that's what telescopes have. For telescopes, you're always looking at something that's really, really far away. Basically, the light's coming in parallel, and so telescopes use a parabolic curvature instead of a spherical curvature. And then it's talking about drawing these ray diagrams. So let's take a look at what a ray diagram looks like. So let's say that we've got, here's the mirror, right? Which is in, to me it looks kind of green or maybe a little bit gray. So here is the surface of the mirror itself. Here is the focal length out to the focal point. And then here is the center of curvature. Now what they've done is they've placed an object right here. So, and they're going to say that the object has a certain amount of height to it, and that's what we start off with in these diagrams. So I've got an object, and what we want to do is draw some light paths. Now, of course, the light's traveling many, many different paths. We want to pick out particular light paths that will guide us in figuring out where the image is going to be located. So starting with the properties of the object, what will be the properties of the image that's created? So here's the object, and we're representing the height of the object here. So the first ray that we draw that's very useful is, let's take a ray that just runs parallel to that principal axis. So we'll have one of the paths where the light comes in parallel. Now what we know from the definition of a focal point is that if light is coming in parallel to that principal axis, that reference axis, it's going to reflect back through the focal point. So hey, I get out my ruler, I get out a pencil, maybe an eraser, and I start drawing this stuff, right? I draw where the mirror is located, I draw where the focal point is, where the center of curvature is, where I want my object to start from, and we can start the object from anywhere. I can start with the object out here. What happens if the object is farther away? What happens if the object is closer in? What if the object is closer within the focal point? And we can use these ray drawings to show what happens in each of those cases. So I hope this is kind of fun, that you actually get a ruler out, pencil out, some paper, and carefully draw these. Now you may be thinking, how do I best represent the curvature of the mirror? And it turns out when we do the ray drawings, we actually are using an approximation. The formulas we work from work under the approximation that the mirror surface can be represented as just being a plane mirror. Even though there's a curvature, if you just draw a straight line for the mirror, that works. The diagrams will work correctly if you do that. So you can draw a little curvature if you want to try that, or you just go with the straight line. Now that first path we've identified, so we need a second path. Just one path of light doesn't tell us where the image will end up. So here's a second path we could try. what if we reverse the order on things? On the first path, we came in parallel, came back through the focal point. On the second path, let's go through the focal point on the way in. That means on the way out, we'll come out parallel. So parallel in, focal point out, or focal point in, parallel out. Those two paths will work. And once I've got two paths, and I've drawn them correctly, so that's the condition here that has to be met. I have to actually have done this correctly. If I've done these two directly, then those 2 points will cross each other. That is the location of the image. Just 2 lines will give me all the information I need. Now, typically we do a third line, which is kind of just we're double checking our work from the first 2 lines. With mirrors, a very useful third line is to draw a line that comes through the center of curvature and then just continues. Now, what that's actually representing is light that reached the mirror, reflected right back. So if I'm looking at light that goes through the center point, then light from the center point would hit the mirror at 0 degrees, which is kind of perpendicular, and then it's going to come straight back. Now, if I'm getting out my pencil and my ruler, that means I actually start from this point, O prime, and put the ruler so that it goes through C. Okay, because before I have to line this up with the center point. Once we do that, if we've done everything correctly, then all 3 lines will cross the same point. And at that point, we're getting pretty confident that we may have done something right. All right. So those are the 3 lines that are easiest. And I'm going to go with these first 2 and say by the time you've got these 2 drawn, just using the focal point itself, not using the center of curvature, you've already got the image figured out. So let's see what happened here. There was an object oriented in this direction, but its image is going to be inverted. So it turns out that there's actually going to be an inversion. Things are going to be flipped upside down. Now you may be thinking, well, is this kind of like the bathroom mirror when I look at something and the left and right are reversed? It's not. So this is different. This is actually something that's flipped upside down. You may have looked at mirrors. If you've played around with curved mirrors, you realize that if you place objects close enough, the images are right side up, but if you move the object farther away at some point, they go upside down. So this is inverted, is what we say. Now, is this image, is it real or virtual? Remember, we had that example before where we said this image with the plane mirror, the stuff you're seeing in the bathroom mirror, the mirrors that you're really familiar with, are always producing virtual images. The images are back behind the mirror, or appear to be, and the light isn't really coming from that location. Now, as long as we got this picture here, the way we keep track of this mathematically is we say that the DI is negative. The DI is over on the opposite side of the mirror. Let's get back to this other example. So in this example, the image actually forms on the side where the light actually is traveling. That's a real image. So this is a real object. A real object means the light really is coming away from that point. So this is the object light spreading out. And then after the reflection, this is the image light coming back together, and in this case, it's forming a real image. There is the formula. Okay, so it's not a trivial geometric derivation, and we're not going to go through it. But this is a formula that if we go in and do some careful geometry on this, and they've got everything lined up here for us, 1 over the focal length is equal to 1 over the object distance plus 1 over the image distance. That works for mirrors, and it works for lenses. So it's very, very useful. Be careful with the formula because it looks pretty straightforward, I just have to invert the D, I have to take it in 1 over and 1 over. Those are inverses. And then I have to remember at the end too that I'm probably going to have to do another inversion to solve for f. So anyway, that's the formula. Get some practice with that, with the homework examples and those in class, in lecture. So the focal length is telling us about the properties of the curvature of the mirror itself. So the focal length simply is 1/2 the radius of curvature of the mirror. The DO depends on where we place the object. So again, I could have a DO that's very close, I could have a DO that's farther away, I could have a DO that's all the way out at infinity. We can move the DOs back and forth. Now what we're also showing here is that in addition to the object and image distances, we want to introduce what's called an object and image height. Those are the H's. So the object has a height, a lateral distance, lateral meaning it's sideways from the principal axis. We want to know how much height it has, and then we can relate that to the height of the image. So F, DO, DI, HI, HO, those are going to show up in all of our examples. Now what we find is that the magnification is defined as HI divided by HO. That makes sense. Now, this is specifically referred to as the lateral magnification. We'll see that it's not the same thing as just because I have a large lateral magnification doesn't mean the image is going to look larger to me. And we'll see what the difference is there. Why is that the case? So, by definition, the lateral magnification is given by HI over HO. And what we can show from the diagram is that HI and HO, that's proportional, HI over HO, is going to be proportional to DI over DO because these are similar triangles. So we can use a little geometry and show that this holds. Now there's a minus sign in the formula. What is that doing there? Well, let's take a look and see. If we look at the example right here, notice how HO, let's go ahead and call that positive. HO is going to be a positive number, but HI is negative. And that's because it's been inverted. So in this case, the magnification would be a negative number. So the negative number here, we plug the numbers in. HI, we plug in a negative value. HO, we're plugging in that positive value. Overall, the magnification is negative because the image is inverted with respect to the object. Now, what about the DOs and the DIs? Well, the DO is positive. The DO is measured from the surface of the mirror out to where the object is located. But the image in this case is also positive. Now, how do I decide positive signs on DOs and DIs? If the object is on the side of the mirror where the light is actually approaching the mirror, that's a positive DO. If an image is on the side of the mirror where the light actually comes together, that's a positive DI. So that's a positive DO and a positive DI. So clearly I've got a problem here because if DI and DO are both positive, then HI will be negative, and kind of vice versa. If the image distance is negative, then this will be positive. So to correct for that, we put a minus sign in there. So that keeps track of the official definition of lateral magnification and the sign conventions we have for DO. So let me just say this too. This formula is reasonably straightforward. What makes it difficult is I got to keep track of DO, is it plus or minus, DI, is that plus or minus, the focal length, is that plus or minus. So those values could be plus or minus, and that's actually where a lot of the work comes in. So let's try this. Let's try another example here. Let's say that we have a concave mirror. Now remember, a concave mirror will be converging. So it's going to be a converging mirror, and we want to find out what the image looks like. Now, it says that the object is a 1.5 centimeter diamond ring. Oh my gosh. It's 20 centimeters from the mirror, and the mirror has a radius of curvature of 20 centimeters, and then the radius of curvature is 30. Find the location of the image, and what is the magnification. So here's a chance for us to go in and determine all those values. Here we go. There it is. There's that formula we're going to be working with for this chapter and the next. All of mirrors, all of lenses. What we can do then is I'm going to write down the given information. So they told us that, and here's my diagram. It's all here. So here is the height of the object. And see, it doesn't matter if it's a diamond ring. All my objects look like triangles. Now, in the slides and in the textbook, they like to use arrows. I think the triangles are handy. See what you think. Try that out. I can draw this triangle pretty quickly with my ruler and then label it as HO. So the HO, they told us, is 1.5 centimeters. The distance from the mirror, and look, I just drew a flat line for that mirror, 20 centimeters. The radius of curvature for the mirror is 30. Now I'm going to use this information to solve for the focal length. Radius of curvature is fine, but what I'm really after is the focal length, because that's what's in my formula. All right, so I first of all can use this formula and solve for DI. So I did. I plugged in these numbers, and I carried out the calculations, and I got 60 centimeters. So at least from the formulas, my formulas are telling me I'm expecting an image that's 60 centimeters away. And then the other formula was the magnification could be calculated as either, depending on what information I'm given, minus DI over DO or HI over HO. Now I know the DI, I just calculated it in part A, and the DO was given. So, and then there's a minus sign out front here. Putting all that together, it says that the formulas are predicting, the math is predicting, the image is located 60 centimeters from the mirror in the direction, it's a positive value, in the direction the lights are traveling away from the mirror. And the object distance was 20, so with the minus sign, that's minus 3. It's predicting that the image will be inverted, and then it will be 3 times larger than the object. And here's my drawing. So what I can do now is I can kind of take all this information, set it aside, maybe not let it bias my results with my drawing. So now I'm going to get out my ruler and draw this. There's the location of the mirror. It's converging. It's a little bit concave, but I just drew it flat. Now one thing to realize too is, to get these drawings correct, you have to scale them along the horizontal axis. Now, the vertical scaling doesn't have to match the horizontal scaling. So for example, the DO here is 20 centimeters, but the HO is only 1.5. If I match the horizontal and the vertical scaling, then my object's going to be just this little tiny thing, and I won't be able to see what's going on very well in my diagram. So I'm going to kind of exaggerate the vertical scaling so that I can actually see the diagram better. Anyway, along the horizontal axis, that's the 20 centimeter mark, and that's the 30 centimeter mark. I'm thinking, gosh, did I really? I don't think I measured this so well. If this is 10 and that's 20, it feels like 30 should be a little farther out. I'm pretty sure I had a ruler out on this one. Maybe it's an optical illusion of sorts. Anyway, to get everything correct, you really do have to measure these out. So here's path number 1, parallel out and through the focal point. Path 2, through the focal point, parallel out. And using my ruler, the 2 lines crossed right there. I didn't draw the 3rd line. I guess I could have done that too. Anyway, what it's predicting is that yes, indeed, I'm going to have an image that is inverted. It's going to be real. The light's really coming together at that location. and it's going to be 3 times the size of the object. Okay, so everything worked out. Ooh, the last thing we wanted to talk about here is HI, from the formula we have here. I can solve for HI. HI is given by m times h naught. The magnification was -3 times 1.5 centimeters gives me -4.5. Okay, so it's a good example. This is a good example. Everything's there. The DOs, the DIs, the HO, the HI, the focal lengths, and the formulas we're going to be working from. What would happen now, this is just a bit different. It says if the object is placed, oh, I see. What would happen if I take the object and I move the object to where the image is, what's going to happen? Now, the DOs and the DIs reverse. So all I have to do is just kind of reverse the direction of the light in these diagrams, and that will tell me that, just wanted to check and see if this is the very same picture. I think it is. So the DOs and the DIs will reverse, and the mathematical formulas tell us that. Because in this formula, I could take the values for DO and DI and switch them, and it still solves the equation. Okay, so the DIs and the DOs reverse. Now, what's going to be different is the magnification. If going from the shorter DO to the longer DI, that gave me a factor of 3. When I reverse the positions, it's going to shrink the image. Instead of the image being 3 times bigger, the image will be 1/3 as large. So I could start with an object out here of this size, and what's going to happen is the magnification is going to be -1/3. There's still an inversion, but it's going to be 1/3 magnified instead of 3 times. So that's what happens if we switch the images and the objects, if we switch the object and image locations. If an object is outside the center of curvature, the image will be inverted, smaller, and real. Ooh, we're going to have to see what we have here. I think they're telling us something incorrect. I didn't catch this when I was going through the notes. So what they're saying here, now this is an example of the object. Well, let's just take a look and see what we've got. Let's ignore what's being said here, because they're actually talking about an object being placed outside the center of curvature. But what they're showing us in the diagram is that I have an object that has been placed inside the focal point. Okay, so what they're saying doesn't match the diagram, so let's kind of ignore what they're saying. If I place the object inside the focal point, let's see what those 3 paths look like. So here is parallel in, and then back out through the focal point. But when I try and do through the focal point, notice I now have to take that line to the mirror as if it's coming away from the focal point. So the light's not going to actually pass through the focal point, but path 2 needs to be aligned such that it lines up with the focal point. So that becomes the key feature, and then it will come out parallel. Now when I do that, what I find is that the 2 paths of light coming away, path 1 and path 2, they're not coming together. So on this side of the mirror, the paths are spreading away from each other, meaning I'm not going to get a real image. I have to follow these paths back to where they appear to be coming from, and they appear to be coming from here. And I can do this with my rulers. The convention here is the path that the light actually took is a solid line, and anything we're using just to show alignments, we use dash lines. So path number 1 comes over here, back through the focal point. Path 2 approaches the mirror in a manner aligned with the focal point, but it didn't really come from there, and then goes back. And then I'm tracing these out as dashed lines. That's where the image is going to be located. That's going to be a virtual image. That's going to be looking like looking in the bathroom mirror, where the image is on the other side of that mirror. All right? And then there's a third path, and we can trace that third path too, and it should line up. So again, warning here, I guess I should go back and maybe cross this out or something. They've written this down for a different example. They've got the wrong diagram, or they've got the wrong description for this diagram going on. Okay, I mean you could try drawing the diagram that they're talking about here. They're talking about a diagram where the object has been placed out here somewhere. What's going to happen, and what they're claiming is that in that case the image will be inverted, smaller, you'll get magnifications less than 1, and the image will be real. Okay, let's continue on with a couple more examples here. So with this mirror, what we are seeing is, where is the... So we have a concave mirror, and the concave mirror is going to be converging. And what they're saying is that we're going to place an object that is 10 centimeters away from a concave mirror. And the radius of curvature here is 30 centimeters. Draw a ray diagram to locate the position of the image. Oh, I see what it is. It's your nose. Okay. All right, this is a little crazy. So I wish they wouldn't have done this. I wish I would have. Yeah, okay. Anyway, here's your nose. And what we're going to do is we're going to take those paths of light. So here is one of the paths that we're going to be looking at. It goes right through the focal point, reaches the mirror, and then it comes back, and it's parallel. So they're, showing what that path looks like. And then they're taking a second path that goes right through, or path number 3, the way it was defined. They're taking it through the center. They're showing an example of using that center point and then letting the light come right back along that path. So the object light is coming from here and here. That is a real object. And then here are the two paths coming out. They strike the mirror. And then the return paths are the image light. And the return paths cross each other at that location. So that's the location of the image. So it's kind of an interesting example. They're taking one particular point here and showing where its image will end up. Now, if this image is is far enough away from this person's eye, then they're going to be able to see the image in focus. But if objects get too close, our eyes can't focus on something quite so close. And in this case, it looks like we're kind of getting pretty close to that limit. Anyway, that's an example of what's going on here is just identifying where that image would be. So it looks like the image is inverted. It's a real image, and the image is actually closer to the person. The image is actually on the positive side of the mirror. It's closer to the person. So if you were looking at a mirror at this image, trying to judge how far away the image is, you would actually see the image out in front of the mirror rather than what we're used to with a bathroom mirror, which would be back on the other side of the mirror. Okay. All right, so let's go ahead and I'm going to go ahead and put those numbers in. Let's see if we can get some more detailed information on this. Also, I think we're coming up close to break, so let me just double check on the time. And we could do that. We could actually take a look. Let me go ahead and write a few things down here just to get started. But we do want to take a break pretty soon here. So this is the object. So I'm going to say this is the location of the person's nose. And what we were told here is that the height of that, or that region of the nose that we're looking at, is 1 centimeter. It's located 10 centimeters away from a concave converging mirror. So the mirror's location is right here. That's 10 centimeters. Now the radius of curvature for this is at 30 centimeters. And again, I'm just using that to determine what the focal length is. So the focal length for this is going to be at 15. So this one looks like it's scaled maybe better. 5, 10, 15. Maybe there's a bit of that same optical illusion as before. So what I could do is I could do the parallel in to the mirror. This is a real object. Parallel in, back through the focal point. That's one path. And then what I'm going to do is I'm going to use the focal point again, rather than center of curvature. So I'm going to get a path that lines up with the focal point, comes in, strikes the mirror. I kind of covered that up with when I added the converging, and then it comes out here. Now this lines right up with this dashed line here, and this path lines up with this dashed line. The image light, the light coming away from the mirror, it's not coming together. It's not going to form a real image. So what I have to do is trace it back to where it appears to have come from, and that's going to give me a virtual image. So this will be the location of the virtual image. Here is DI, and DI will be a negative number. So DI is going to be a negative number, DO is going to be positive, and what I can see is HO is a positive number, and HI, which I haven't labeled, but HI is here, HI is also going to be a positive number. There's not an inversion taking place here. So, plugging into the formulas, just taking the numbers that we've been given for the focal length and for the object distance, it gives us an image distance at negative 30. Now I'm looking back at my diagram that I've drawn, and I'm thinking, yeah, that's very encouraging. It does appear that negative 30 is a perfectly reasonable distance to, let's see, this was what? Positive 10, so 10, 20, 30, yeah, it really does look like about 30. Okay. In fact, if I do the drawing carefully like I have, I can take my ruler out and actually get a pretty good estimate by setting my ruler there and using the drawing itself to get an idea of what DI is equal to. All right, so that seems good. The other item is we want to do the magnification. Now that's going to be minus DI over DO. DI is a negative value, so this is going to go positive, and it looks like the magnification then is going to be equal to 3. So I'm going to get a magnification of 3, and then the HO then is predicted to be 3 times the HI is 3 times HO. So if this, the vertical scaling, if that's 1 centimeter, this should be 3 centimeters. Yeah, it seems reasonable. All right. So everything checks out, and that's kind of the approach that you want to take on these problems. I would suggest is kind of go back and forth. Write down the given information. Maybe get a drawing started. See how far you can take the drawing. Maybe you complete the drawing and you come back and double check the numbers. Or maybe you get stuck somewhere along here and you start to calculate some numbers here. Work back and forth and just check to make sure that everything is remaining consistent. I'm going to go ahead and stop there. Let's go ahead and take a break for 10 minutes or so, and then we'll be back.